Hi everyone. In this video, we'll continue to talk about the margin of error. We'll spend a little more time talking about the theory and the idea of the margin of error, and then we'll actually get into how it's calculated. We'll be going over a PowerPoint slideshow on the topic of the margin of error, but before I get into the PowerPoints, I wanted to do a demonstration right here in which I'm sampling from a made-up population. I think this demonstration will help explain the margin of error in a little bit more detail. So let's imagine that we have a made-up population of 800 people right here, and these are their ages. So maybe we could pretend that this population is at a university that has 800 students. It would be kind of a small university, but we'll just say that it's a university that has 800 students, and these are their ages. So here are all the 20-year-olds right here, or here are all the people in their 20s. The people in their 30s are right here, people in their 40s, and people in their 50s. And let's say that the youngest person is 20 and the oldest person is 59 right here. And it looks like this population is positively skewed or skewed to the right because most of the population numbers are down at this end and there's fewer and fewer up here at this end. Maybe I'm interested in what the mean age of this population equals. I'm interested in what the mean age of the 800 students at this university equals. And let's pretend that I don't have enough time to actually give out a survey to all 800 students and ask them their ages. So instead, I take a random sample of students and I record their ages, and then I calculate the mean age of my sample to estimate the mean age of the entire population. And we'll actually go through a demonstration in which I use Excel to take a random sample from this population and record the ages of my sample. But before I actually take my sample, I'm going to actually find out what the mean age of this entire population equals. I can do that because it's really just a made-up population. It's not a real population. So what I did right here in Excel is I made up 800 numbers in column A, and these 800 numbers are the 800 ages of the people in this made-up population. What I can do is I can go down here to the bottom after the 800 population number, and I can use Excel to calculate the mean age of the population. So down here in row 802, I'll type in equals average, and then put the left parentheses right there. And then I can type in A1, capital A1, then a colon, then capital A, 800. So it's equals average, parentheses, A1, colon, A, 800, and then the closing parentheses. Once I press enter, it'll add the 800 numbers and divide the total by 800 to get the mean or the average of this made-up population. So it turns out that the mean age of this population is 34.8 years when I round it off to one decimal place. So that's about right here. Let me double check that again. So it's 35.8 years. Remember that the symbol for population mean is the Greek letter mu, which looks sort of like a U. So it's mu is 35.7. or 35.8 rounded. Remember that I, as a researcher, don't know that this is what the population mean equals because I don't have time to record the ages of all 800 people in the population. What I'm going to be doing in my study is taking a random sample and of people from the population and recording the ages of the people in my sample and then calculating the mean age of my sample to estimate what this population mean equals. So now let's actually use Excel to take a random sample of the population. You might be wondering what these red numbers are in column B. They're actually just randomly generated numbers. They're just numbers that Excel randomly created. But what they're going to be used for is to randomly shuffle these 800 ages that I have in column A. So what I need to do first, before I can take a random sample, is I need to decide what sample size I'm going to be using. Let's say maybe I want to select 36 people. There's actually a reason why I chose the number 36. I'll explain it to you a little bit later. So what I need to do is I need to type in equal sign right there, and then click on the first age in the population, and then press enter. Then I can put the mouse above the bottom right corner right here and drag this down to row 36. And now what it's done is it's taken these first 36 ages right here and it's moved them over, or it's copied them into column D. So these are just the same 36 ages that we have over here. But this isn't actually a random sample of 36 people because it's the lowest 36 people in the population. But if I shuffle these 800 ages randomly, then these first 36 numbers actually will be a random sample. Now let's shuffle the ages right now. I can do that by highlighting column A and column B. And then clicking on sort to sort the values. So remember that all the numbers in column A are the ages of the 800 population members. They're the actual numbers we're interested in, and these numbers in column B are just random numbers that came from Excel. So you can't see what I'm doing right now, but I'm going to click on sort, and then I'm going to sort by column B, and then click on OK, and then it randomly shuffles these numbers. So now these are still the first 36 numbers in the column, but now they're a random sample of the population. So you can see that they're still the first 36 numbers because this is the same as this, this is the same as this, this is the same as this. So it's still the first 36 numbers in this column right here. But like I said, it's now a random sample of 36 people. So let's pretend that I just took a random sample of 36 people from the population, and I did a survey in which I recorded their ages, and these 36 ages right here are the data set that I recorded in my study. They're the 36 numbers that I actually recorded. And now what I want to do is I want to calculate the mean of my sample. I'm going to calculate the mean of the 36 ages that I recorded from my sample. And I can do that if I need to click on a blank cell down here, like I did last time, and type in equals average, and then put a left parentheses. Then type in, well, now I'm in column D, so D 1 colon D 36, and then close the parentheses, and it'll give me the average of these 36 numbers right here. So the mean age of the 36 people in my sample is 38.9, rounded. And the population mean, which is actually unknown to me as a researcher, is 35.8. So my sample mean actually did do a pretty good job of estimating this unknown population mean, because my sample mean is about 38 and the population mean is about 35. So my sample mean is pretty accurate. My sample mean overestimated the population mean by a little bit, but not by very much. So my sample mean is 38.9. So like I said, 38.9 is a little bit above the population mean, but not by very much. And this sample of 36 people that I selected is just one possible sample of 36 people that I might have selected. There's other possible combinations of 36 people that could have been chosen, and each of those different combinations of 36 people would have its own sample mean. And the sample means of all possible samples of 36 people are under this sampling distribution curve right here. So down here are all of the samples that would have given me a low sample mean, and up here are all of the samples that would have given me a high sample mean. And here in the middle are all of the possible samples that would have given me a more medium sample mean. But under this curve are all of the possible samples of 36 people that could have been chosen. So right here I'll put n equals 36 just to show that these are all the possible samples of 36 people that could have been chosen. And when the population that you're sampling from is normal, or when you're taking a sample size of 30 or higher, then the sampling distribution has at least a roughly normal shape, like what we see right here. Now the population that I'm sampling from definitely isn't normal, because it's positively skewed. There's more people at this low end down here, and fewer people up here. But even though the population that I'm sampling from is skewed, I took a sample of 30 or higher. I took a sample of at least 30, which means that even though the population is skewed, the sampling distribution will still be at least roughly normal, like it is here. So the fact that I took a sample of 36 people means that this sampling distribution will be roughly normal, even though I sampled from a skewed population. When the sampling distribution is normal, the population mean is at the center. It's right at the center of the sampling distribution. So the population mean, which is the mean age of all 800 people in the population, is at the center of this sampling distribution. And right here, above 35.8 would be all of the possible samples of 36 people that would have given me a sample mean of 35.8. So right here is a group of 36 people that would have given me a sample mean of 35.8. And right here is a different possible sample of 36 people that would have given me a sample mean of 35.8. And right here is another possible sample of 36 people that would have given me a mean of 35.8. So these are different. These are different groups of 36 people. Um, this is one group of 36 people. This is a different group of 36 people, and this is a different group of 36 people. And even though they're different groups of people, they all have a mean. Each of them has a mean of 35.8. That's why they're all stacked above 35.8. So if I got this sample, my sample mean would come out to 35.8. Sorry, if I selected this sample, my sample mean would be 35.8. If I selected this sample, my sample mean would be 35.8. And if I selected this sample, my sample mean would also be 35.8. And there could be some people in this sample that are also in this sample, and there could be some people in this sample that are also in this sample. In other words, these samples might overlap each other, but the idea is they're not the same exact group of 36 people. They're different combinations of 36 people. So if I happen to select one of these samples right here to be my actual sample, then my sample mean will be a perfectly accurate estimate of the population mean. Because if I happen to select any one of these samples right here to be my actual sample, my sample mean will come out to exactly the same number as the population mean, which is 35.8. Now, my sample mean didn't come out to 35.8. It came out to, I think, 38.7. So I didn't get one of these samples right here. My sample mean was a little bit higher up here somewhere. So let's look at 35.8. I'm sorry. My sample mean was 38.9. So right here we have all of the possible samples of 36 people that would have given me a sample mean of 38.9. And my my actual sample is just one of those samples right here. It could be any of them, but it's just my actual sample is in here somewhere. The sample that I actually selected. Now, just to help make the point clear that there's more than one possible sample that could have been chosen, when I'm going to repeat my study and randomly select a different group of 36 people. And to do this, I'm just going to reshuffle the 800 population members. So right now we're imagining that I'm a researcher who's repeating my study. I'm going out to select a different group of 36 people, and I'm going to record the ages of my new group of 36 people. And this will show you that when you repeat a study with a new sample, you get a result that's not exactly the same as what you got the first time. The results always change a little bit from one sample to the next. So I'm going to sort by column B again to reshuffle. So now this is a new group of 36 people since it's been reshuffled. It's not the same group of 36 people anymore. Now, there might be some people who were in the first sample who were also in this sample, but the idea is this isn't the same exact group of 36 people anymore. There's at least someone in here that wasn't there the first time. So it's a different sample of 36. And this time, the sample mean came out to 36.4. So this group of 36 people has a mean age of 36.4. So let's see where 36.4 is. Well, if 35 is right there, 36.4 is about there, and my new sample mean is one of these. My new sample is one of these samples that's right here above 36.4. Because right here would be all of the possible samples that would have given me a mean of 36.4, but my sample is just one of those samples in here somewhere. So this was my first sample. This is now my second sample. So this sample is a little bit more accurate than my first sample was because my second sample had a sample mean closer to the population mean. My first sample had a sample mean that was a little bit further away from the population mean up here. So now I think we understand the idea of the sampling distribution and how under this curve we have all possible samples of 36 people. So now let's actually get into the idea of the margin of error. I'm going to explain the 95% margin of error. So before I explain the 95% margin of error, we need to divide this sampling distribution into three areas. So down here we have the lowest 2.5% of the possible samples. So out of all of the possible samples of 36 people, these samples down here would give us the lowest sample means. These are the most extreme samples at the low end. So if I end up getting a sample with a sample mean down here, my sample mean is going to be far below the population mean. I'm going to be underestimating the population mean by quite a bit. Up here we have the highest 2.5% of the possible samples. So I said that if I end up selecting a sample of 36 people with a sample mean down here, I'm going to be underestimating the population mean by quite a bit. If I happen to select a sample of 36 people with a sample mean up here, I'm going to be overestimating the population mean by quite a bit. Because these samples down here have sample means that are far below the population mean. These samples up here have sample means that are far above the population mean. And so here's the lowest 2.5%. Here's the highest 2.5%. Here we have the the middle 95% of the possible samples. Here we have the lowest 2.5% of sample means. Here we have the highest 2.5% of sample means. And all of the sample means that are in between are in the middle 95% right here. And as a researcher, I hope to get a sample mean in the middle 95% because I don't want to end up with an extreme sample down here or an extreme sample down here because my result won't be very accurate. I'm hoping to get a sample mean that's at least fairly close to the population mean that I'm trying to estimate. So right here, we have the lower boundary of the middle 95%. Right here, we have the upper boundary of the middle 95%. And what this line right here is going to be showing is the distance from the population mean to the lower boundary of the middle 95%. And this line right here is going to be showing the distance from the population mean to the upper boundary of the middle 95%. And if the sampling distribution is normal, or at least roughly normal, like it is here, then it turns out that this distance and this distance are the same distance. So if the sampling distribution is normal, then the distance from the population mean to the lower boundary is the same as the distance from the population mean to the upper boundary. This distance right here is the same as this distance right here. Because, well, the shape is symmetrical. This side is just the mirror image of this side, so this distance and this distance have to be the same number. And that distance is called the 95% margin of error. And it turns out that if the sampling distribution is normal or bell-shaped like it is here, then the 95% margin of error can be calculated. I said that this sampling distribution right here is normal or bell-shaped, or at least roughly normal because the sample size was above 30. If the sample size is 30 or higher, the sampling distribution is normal, even if the population that I'm sampling from is skewed. So since the sampling distribution is normal, we can actually calculate the 95% margin of error. And I'll explain the steps we need to go through to be able to find out what it equals. Before we can find out what the 95% margin of error equals, we need to calculate one other value called the standard error. What the standard error is the standard deviation of all sample means inside of the sampling distribution. So there's actually a formula that can be used to calculate the standard error, and I'll show you how to do that. And then once we get the standard error, we can use the standard error to get the 95% margin of error. So the reason why we need to find out the standard error is because it turns out that if the sampling distribution is normal, like it is here, this boundary is 1.96 standard errors below the population mean. And this boundary up here is 1.96 standard errors above the population mean. And you might be wondering why that's the case, but it just turns out that if the sampling distribution is normal, then this is 1.96 standard errors below the population mean, and this is 1.96 standard errors above the population mean. So once we find out what the standard error equals, we can multiply the standard error by 1.96, and then that will actually tell us what the 95% margin of error is. So the steps to get the 95% margin of error are just to find out what the standard error equals, and then multiply that by 1.96. Now, the formula for the standard error is just the population standard deviation, meaning the standard deviation of all 800 people in the population, divided by the square root of the sample size. So in order to find out what our standard error equals, we need to find out what the population standard deviation is, sigma, and then divide that by the square root of our sample size. Then we'll have our standard error. Then what we can do next is multiply that standard error by 1.96, and we'll get our 95% margin of error. We can calculate the population standard deviation by just using Excel. I'll show you how to do that using Excel. So I said that these are the ages of the 800 people in this made-up population. All of those ages are in column A. I'm just going to go down to the bottom of the column, and then I'm going to calculate the population standard deviation. Remember, this was the population mean, or the average of the population. So I'm going to calculate the standard deviation right below the population mean. So I just type in equals ST DEV point P. Point P means population. And then put a left parentheses, and then type in capital A1 colon capital A 800, and then close the parentheses. And Excel will calculate the standard deviation of all 800 ages in the population. And the reason why I had to put a point P right here is because remember that when you're calculating the standard deviation of an entire population, like I am here, there's no n-1. There's no you're not using the adjustment that you would use for a sample standard deviation. That's why it has to be point P. So now I'm going to press enter, and it's going to calculate the standard deviation of the population, and it's 10.9 roughly. So the standard deviation of the ages of all population members is 10.9. That's sigma. Now I'm going to divide this sigma right here, population standard deviation, by the square root of my sample size. Well, remember in my study, I was taking a sample of 36 people, which means that my sample size was 36. So I have to divide by my sample size of 36. I'm sorry, I actually have to divide by the square root of my sample size of 36. So 36 goes under the square root sign. So it's the population standard deviation, meaning the standard deviation of all 800 ages, divided by the square root of my sample size of 36. That's the standard error. Now, I can just use a square root key on a calculator to get this square root, but and it's going to come out to 6. The reason why it comes out 6 is because when you multiply 6 times 6, it comes out to 36. So really, all a square root is just a number multiplied by itself to get another number. So in order to get the number that you multiply by itself to get 36 is 6. That's why the square root of 36 is 6. It's just like how 3 times 3 equals 9. And since 3 times 3 is 9, the square root of 9 is 3. So 36 square root key is 6, which means that I just have to divide 10.9 by 6. Because like I said, this came out to 6. So 10, I'll do that with my calculator. 10.9 divided by 6 is 1.8, roughly. That's my standard error. So it turns out that the standard deviation of all of the sample means under this curve is 1.8. Because like I said, the standard error, all the standard error is just the standard deviation of all sample means inside the sampling distribution. Now we can use our standard error of 1.8 to get the margin of error. I said that this upper boundary right here has to be 1.96 standard errors above the population mean. So what we have to do is multiply 1.96 by our standard error of 1.8. And it comes out, when we multiply, it comes out to 3.5. That's the 95% margin of error. So overall, if you want to get the 95% margin of error, you just calculate the standard error, like we did here, and then you just multiply 1.96 by the standard error, and that gives you the 95% margin of error. So it's just a two-step process. So the 95% margin of error is 3.5. This is 3.5. This distance down to the lower boundary is 3.5. This distance up to the upper boundary is also 3.5. Now let's actually find out what number this boundary actually is, and what number this boundary actually is. So we know that we just found out that this boundary is 3.5 below the population mean. So if we subtract our population mean by our margin of error of 3.5, we'll get this boundary down here. Minus 3.5 is 32.3. So since this boundary is 32.3, that means this lower tail down here includes all of the possible samples of 36 people that would give us a sample mean below 32.3. All of the sample means inside this lower tail down here have a sample mean below 32.3. So that means that if we took another random sample of 36 people from our population and calculated the sample mean again, and the sample mean came out to a number below 32.3, that would tell us that our sample mean is in the lower tail down here. For example, if our next sample mean came out to 31.7, that would be in this tail down here. Or if it came out to 29.8, that would be in this lower tail, because that would be a sample mean below 32.3, below this lower boundary. Now let's find out what number is at this upper boundary. To do that, we have to take the population mean and add the 95% margin of error. So take the population mean, add 3.5, and we get 39.3. So any sample of 36 people that would give us a sample mean above 39.3 would be in the upper tail up here. So if I took another sample of 36 people and calculated the sample mean, and the sample mean came out to 42.3, then that sample would be in the upper tail, because that sample has a sample mean above this upper boundary right here. Or if the sample mean came out to 39.8, that sample would be in the upper boundary, because that sample would be in the upper tail up here, because it would have a sample mean above this boundary. Now let's actually look at the two samples that we actually selected and let's figure out if these two samples really are in the middle area, in the middle 95%. Well, if the lower boundary is 32.3 and the upper boundary is 39.3, then both of these samples are in the middle 95%, because these two samples that we selected both have a sample mean that's between 32.3 and 39.3. Remember, our first sample mean was about 38.5, and our second sample mean was about 38.9. Both of those are in between these two boundaries. Now let's take one more sample of 36 people and calculate the sample mean, and see if we get a sample mean in the lower tail, in the middle 95%, or in the upper tail. So I'm just going to reshuffle again to take another random sample of 36 people. So now it's like I'm a researcher who's repeating my study a third time with the same sample size. I'm going out and taking a third group of 36 people and recording their 36 ages. So now I have a new group of 36 people. I've recorded their 36 ages, And this time my sample has a sample mean of 33.6. The mean age of 33.6. Well, that's about right here. So right here we have all of the samples that would give us a sample mean of 33.6, and my selected sample is one of these samples in here somewhere. I'll just put it down at the bottom. And my third sample right here, my third selected sample, is in the middle 95% because the lower boundary is down here at 32.3. So far, all three of my samples that I've selected are all in the middle 95%. And that brings up an important point. If I kept selecting more and more samples of 36 people over and over again, and I kept calculating the mean of each sample, it turns out that 95% of the time, the sample mean would fall in the middle 95%. It would only fall in the lower tail 2.5% of the time, and it would fall in the upper tail 2.5% of the time. So I already explained that this is the lowest. This contains the lowest 2.5% of samples. This is the middle 95% of samples, and this is the upper 2.5% of samples. It turns out that if you repeat the study over and over again, you get a sample mean down here 2.5% of the time, in here 95% of the time, and up here 2.5% of the time. So I've explained the idea of the 95% margin of error. It's the distance from the population mean to the lower end and the upper end of the middle 95% of the possible samples. And it's also the distance from the population mean to the lower end and the upper end of where the sample mean falls 95% of the time. Because, like I just explained, if you repeat the study over and over again, the sample mean will fall in here. It will fall between the two boundaries 95% of the time. So I think I'm going to move on from talking about the 95% margin of error to talking about a margin of error with a different percentage in front of it, because it's actually possible to calculate a margin of error with a different percentage in front of it. The 95% margin of error is what's typically calculated in actual research, but it's possible to calculate a margin of error with a different percentage. And I'll explain how that can be done. So what if we had a boundary right here, a different lower boundary, and a different upper boundary right here. And 90% of the possible samples are between these two boundaries, between these two blue boundaries. Well then, if that's the case, then the distance from the population mean to this boundary and the distance from the population mean to this boundary would be called the 90% margin of error. It would be the 90% margin of error because it's the distance from the population mean to the lower end and the upper end of the middle 90% of the possible samples, not the middle 95%. Now, I explained how to calculate the 95% margin of error, and you might be wondering, how would we calculate the 90% margin of error? Well, we can calculate it using a similar formula. I said that when the sampling distribution is normal, this boundary is 1.96 standard errors below the population mean, and this boundary is 1.96 standard errors above the population mean. It turns out that 95% of the possible samples fall between these two boundaries. But it also turns out that when the sampling distribution is normal, like it is here, the lower end of the middle 90% is 1.645 standard errors below the population mean. And the upper end of the middle 90% is 1.645 standard errors above the population mean. So what that means is that just like how we multiplied the standard error by 1.96 to get the 95% margin of error, we can just multiply 1.645 by the standard error, and we'll get the 90% margin of error. So it's going to be the same steps that we followed last time. The only difference is instead of multiplying by 1.96, we're going to be multiplying the standard error by 1.645, a different number. So let's see what that equals. We have to multiply 1.645 by our standard error, which we already know is 1.8, and it comes out to 2.9, roughly, or about 2.96. So our 90% margin of error is about 2.96. So the distance from the population mean to the lower end of the middle 90% is 2.96, and the distance from the population mean to the upper end of the middle 90% is also 2.96. It's actually possible to calculate a margin of error with any percentage you want. I could calculate a 68% margin of error. I could calculate a 75% margin of error. I could calculate a 36% margin of error. And it turns out that for every possible percentage that you could, for every percentage that you could use, there's a number that goes along with it, and that number has to be multiplied by the standard error. So if you want This number that we're multiplying by the standard error to get the margin of error is called a confidence coefficient. And there's a confidence coefficient for every percentage. So here's some examples. For a 90% margin of error, the confidence coefficient is 1.645. For the 95% margin of error, it's 1.96. And for the 99% margin of error, it's actually 2.58. So all a confidence coefficient is the number that you multiply the standard error by to get the margin of error. And so this is the confidence coefficient for a 90% margin of error, meaning if you want a 90% margin of error, you multiply 1.645 by the standard error. If you want a 95% margin of error, you multiply 1.96 by the standard error. If you want a 99% margin of error, you multiply 2.58 by the standard error. So each of these confidence coefficients in here is just a number that you multiply the standard error by to get the margin of error. So the formula for the margin of error is just the confidence coefficient multiplied by the standard error. And you might be wondering where I got these confidence coefficients from. Well, it turns out that they can actually be looked up in a table. So if you want to calculate a margin of error, what you have to do is you have to look up the confidence coefficient in the table and then multiply that confidence coefficient by the standard error, and you get the margin of error. So if I wanted to calculate let's say the 70% margin of error, I would just go to a table and look up the confidence coefficient for 70%, and then multiply that by the standard error, and I would get my 70% margin of error. And then what that number would be is just the distance from the population mean to the lower end and the upper end of the middle 70%. If I wanted the 50% margin of error, I would just look up the confidence coefficient for 50%, multiply it by the standard error, and I would get the 50% margin of error. And what that would be is just the distance from the population mean to the lower end and the upper end of the middle 50%. So I think this is a good starting point. Now I'm actually going to go into the PowerPoint slideshow that I have for this week's topic.